All right, we can begin. So first of all, any questions from anything so far in the course? Everything's clear? All right, so today I want to begin by talking about bounds on curvature, and then I want to talk more about the energy momentum tensor, as I promised from last time. Okay, so we're going to introduce what people usually call the critical density. So let's just define rho crit as defined by the Hubble parameter. It's going to be this thing. Okay, that might seem a bit peculiar, but the reason that this thing is useful is if you recall the Friedmann equation from last time, we had that Hubble squared is 8 pi g over 3 rho over c squared minus the curvature. Okay, and what we want to do is a couple of things. We want to, well, basically this rho critical, if you can see what's going on here, it's defined so that if rho were to equal rho critical, this number, these two terms would balance. This would just collapse to h squared, right? You plug that value into there. And that would be critical in the sense that it must mean that the curvature is zero. Does that make sense? That's what's critical about it. It's if you were to look at the universe and find that the density happens to equal that number, in other words, the density and h are related in this special way, the universe self-consistently has to be flat. And that's a kind of critical case between open and closed. And so we can just rewrite this equation using rho. And so what people usually do is you go through, you divide by h squared. So you get 1 would be 8 pi g over 3 h squared c squared rho minus k c squared over a squared h squared. And then I just put in rho critical here. Okay, so that whole thing is rho critical in the denominator. And then usually people define this capital omega as this ratio, rho over rho critical. So a dimensionless measure of density. And then our equation just becomes, we can write it as omega minus 1, move things to the other side, is kc squared over a squared h squared. Okay, so it's good to have generally sort of dimensionless measures of things. You don't want to, in cosmology, drag around all the C's and the G Newtons and the Hubbles, and they're all wildly different value depending on your units. But here we have this omega is some dimensionless measure of density, normalized to the critical density. And we see that if it happens to be 1, as I said, that's the flat universe. That's just a rewriting. Is that okay? And so we could summarize from this equation, omega less than 1 is rho less than rho critical, which requires a hyperbolic universe with negative curvature. Roughly, it looks like this is the geometry. Omega equals 1 is the special case rho equals rho critical, no curvature, flat. And then omega greater than 1 is where we're greater than the critical density, positive curvature, which means spherical. Okay. So that's fine. So now we want to think about, well, any questions about this? So now we want to think about how might we observationally constrain the amount of curvature in the universe. And so things look pretty flat on large scales. And so the best way, like if you're on the Earth, as we are, the best way to check on, if you're on some funny geometry, let's say you were on the sphere, okay, but you couldn't go around it, let's say, locally you could imagine just drawing triangles and checking if these triangles have some peculiar property, like that the angles add up to more than 180 degrees, things like that. Okay, so the best way to constrain the curvature is to form triangles and measure their properties, but then you don't want some tiny small triangle, then the angles will add up to almost exactly 180 degrees. So you need the biggest triangles possible that you can think up. And so the biggest ones we can think up involve looking at the cosmic microwave background radiation. And so this we're going to discuss later in the course. So I don't want to get into all the details right now. But just to say that when we look at the cosmic microwave background radiation, it's not perfectly homogeneous and isotropic, even though we're working in that approximation here. But the slight departures are things we're very good at measuring. And those departures you can think of as waves. The matter in the universe has little waves in it, small deviations from homogeneity. And those waves have certain characteristic wavelengths that we can have, what we can predict by some basic theory. Okay, because if you go back to the CMB, this is when the universe was at a time about 380,000 years old. And at this era, the conditions were such that, it was relatively hot, about 1,000 times hotter than the 2.7 Kelvin now. So it's, say, 2,700 Kelvin or so. But this is very mild compared to what we understand in modern physics. Okay, so we understand the conditions very well. The physics here is not in some speculative regime of quantum gravity or anything fancy. So this is a very well understood regime. And it's a long story that we could talk about later in the course. But knowing the physics of how, say, essentially electrons interact with photons and so on, and some basic gravity in that regime, there are certain wavelengths that are amplified more than others. So there are certain characteristic scales. So let's just say there's a length scale, we'll call it a physical length scale, that we can predict. And then we can look to see if the scale of those wavelengths that are amplified matches L physical or not, or is it bigger or less? So we can draw a little picture associated with that. Okay. So let's say you had, we'll start with, say, positive curvature, things being spherical. Right, so you're living on a spherical universe. You can imagine that when you're on a sphere, right, even if you start with parallel lines, they go out and they tend to converge. So there's focusing. Okay, so this means that if, let's say, this is L physical, and that we're standing over here, so here we are looking back at the CMB, so it travels billions of light for billions of years to get to us. If it's on a sphere, the light would do something funny. Let's say it comes in like this to us. Right, there was some focusing going on. Okay, so we look back, and therefore we would trace back and say, oh, the top end is up there and the bottom end is down there. So it would look, here's if that's blue. Let me draw this blue. It would look like it was up there and down there. Okay, so this length here would be like L apparent. That's the apparent size of this thing. Is that all right? So we check. Basically, we measure this angle here. You measure the angle, and you check what you get. And so forth, right? So, and then the opposite case well, k equals 0 flat, it's all very boring. These blue and black lines that I drew would just overlap each other. There's nothing interesting going on. And the opposite case, if k is negative, you have hyperbolic geometry. This is L physical. So these are supposed to be the same. My blues are supposed to be the same. Now there's a diverging curves going on. So to draw that, it would be something like this. It kind of goes up, and this one goes down. Hard to draw that very well. Okay, so lines would come in like this, rays of light. And so this would look, I made it look like the angle is 0. Okay, I didn't draw it very well. But the apparent size, let's say, of this one, let's say here. So say L apparent would then be very small. Okay, so that's what we can compare. Questions about this? No. Okay, so observations then, we haven't seen either of these scenarios. Observations are compatible with it just being flat. Okay, so L physical and L apparent are the same with current measurements. Let's summarize that up here. Right, so the observational bound is something like that. This omega that I defined, we can just put in absolute value, is less than something like 10 to the minus 3. And I put a little 0 here to indicate today. Made the measurement today. Okay, so the rho today, if you like, the rho is matching rho critical to at least 1 part in 10 to the 3. There are 3 significant figures, and maybe more, because this is just the bound. So that says that, or said k c squared over h squared a squared. That was the piece that this thing equals. And if I put zeros here, that means today. This is less than 10 to the minus 3. I should put an absolute value. The only thing here that could be negative is k, because it could be hyperbolic. So that is the same as writing this. Okay, so we can use this and to make it sound a little more physical, right? So, well, first of all, as a percentage, we care about this. We want to know that the curvature is at most contributing 1 part in 10 to the 3 to the Friedmann equation. Okay, so if you just drop the curvature term, at worst, you're making 1 part in 10 to the 3 errors today. May not be the same in the future or the past. We can talk about that in a minute. But today you would be doing things right at 1 part in 10 to the 3. But let's convert this now into an actual length scale. So let's say this thing were a sphere where the curvature here was at the upper bound of 10 to the minus 3, for example. How big would that sphere actually be? Okay, so that would be a lower bound on the size of the sphere. We can do that. So often today, this scale factor, we often choose it to be 1 today. That's just a convention. I think I mentioned this last time. Right? So the scale factor, you can think essentially at the Big Bang, A goes to 0, and then it grows as the universe grows, and then we can say without loss of generality that today it's equal to 1. And that way today, x, our coordinates, equals x physical. It's much nicer than having some other convention. But anyway, if we do this, and then I'm going to write the curvature. Remember, this is 1 over the radius squared. Let's just do magnitude to incorporate the hyperbolic case. And then let me define the Hubble length. So you recall, maybe from the first lecture, right? 1 over h naught Right? H naught has units of inverse time, it's a rate. So 1 over H naught is called the Hubble time. So naturally enough, the Hubble length, we can get a length out of this if we multiply by c. And that will, I'll call that dH. That's the Hubble length today. That's a useful length scale. And you remember the Hubble time, by just taking 1 over h, was 14 billion years. Remember that from first lecture? 1 over h naught is about 14 billion years. So I don't have to work too hard. C over h naught, therefore, is 14 billion light years. Okay, so I immediately know what that is. So this is about 14 billion, all right, L years, light years. Okay, so that's useful because the C over h naught squared is appearing in this formula. And so we obtain putting this into here, we obtain Hubble length, today's Hubble length, dH squared. The K I'm going to trade in for 1 over R squared. This must be less than 10 to the minus 3. Okay, so this implies a bound on the radius of the sphere. It's therefore greater than 10 to the 1.5, if you like, the Hubble length. Okay, so it's greater than, so 10 to the 1.5, that's like 32 dH. And that's already 14 billion light years. So we learn that the radius of the sphere today must be greater than, well, you do 14 times 32, that's something like 450 billion light years. Right? So if our universe is a sphere, it's at least that big. So right, so cosmology, we're often interested in length scales like this, the Hubble length, for good reason, on the order of 10 billion light years and smaller. But the flatness approximation is so good that even on the whole, out to the Hubble length, it will look very flat, even if it were down at the minimum possible, which is 450. And as far as we know, this RS might actually be infinity and the universe may just be flat, or completely flat. All right, now I want to talk, unless there are any questions. Okay, that's, we're going to talk about that as we go. But 1 over h, which is what I call the Hubble time, is on the order of the age of the universe. But it's not by definition the age of the universe. Okay, so actually, maybe I can sneak that in 1 minute, just to clarify that point. Okay, so let's think now about the time dependence of this thing. Yeah, so the fact that 1 over h is 14 billion years and the age of the universe is 14 billion years is a slight coincidence. Like the fact that it worked that well. Okay, but the fact that it's the right order of magnitude is not a coincidence. I'll clarify in a minute. But this curvature, there's a lot of people, when they look at, say, okay, the fractional contribution of curvature to this equation is at most 10 to the minus 3. It's important to note, as I said, that this number here is the bound today. So what does that imply, let's say, for the early universe? Okay, well, what it implies, will anyone have any thoughts about that? Do we think, if I were to reevaluate this in the early universe, what's going to happen to my bound here? Is it going to be tighter bound, weaker bound?
Just to clarify,
yeah.
Is that value gotten from evaluating the values of the equation, or is it from doing this geometry?
Oh, it's from you do that geometry, and once you get out, you do this measurement. So from that measurement, you learn this number, 10 to the minus 3. Now, given this fact that it's bounded to be 10 to the minus 3 from this observation, there's nevertheless, if I look at omega minus 1, instead of evaluating it today, this number can evolve. Okay. Let me be clear about that. So omega minus 1, that with magnitude, is equal to the magnitude of k c squared over h squared a squared, right? And in general, these things depend on time. So we know that this thing is at most 10 to the minus 3 today. Given that fact, if we know how h and a evolved, we can convert that into a bound at different moments in time. Okay. So this thing, presumably, is, you can think, is this going to grow or decay in time? It may do one or the other. Well, in fact, I have to be careful here. We cannot answer that in general because I have to tell you the stuff that fills the universe. Okay. But let's say we just, they give us a flavor for this issue. Let's go back to the case that we already studied in the first lecture. So if you have non-relativistic matter, then our Newtonian analysis is correct. Okay. So for non-relativistic matter, you recall we learned that R is proportional to T to the 2/3. Remember this? If we're flat. But we know that we're almost flat. So this is very close to being correct anyway. Does that make sense? We're going to see as we go to the early universe, this will become even better and better. That will be the punchline of this 2-minute calculation. So using the flat approximation is going to be very good. That will not be a problem. And when we go to general relativity, the correspondence we said was R is basically proportional to the scale factor. Okay, so instead of using R, we're going to use the scale factor. That means that is proportional to T to the 2/3. Okay, so that's how the scale factor grows if the universe is dominated by non-relativistic stuff, dominated by stars, galaxies, dark matter. It does this. Okay? Now, so if I want to be fancy about it, I could write A equals A naught T over T naught to the 2/3. That just locks down the constant proportionality. And then Hubble, which is A dot over A. Well, if A is T to the 2/3, Hubble is just a simple derivative. You pull down a 2/3, and then you take A dot divide A. So you get a 1 over T. I hope that's clear, right? The derivative gives you 1 over T. So from this, these pair of formulas here, you can predict the time dependence of this thing. Okay, these are constants, and then H goes like that, and A goes like that. Now let me, maybe I'll squeeze in a comment here about Tony's question now that I have the relevant equation on the board. Okay. So this is something we're going to discuss later in the course, especially in the context of dark energy. But you see this little equation here, H is 2 over 3T. We can invert that to write T equals 2 over 3H. So therefore you see that 2 over 3H naught would be the prediction. If I put a naught there, that means the current value of H. This would predict the age of the universe, T naught equals this. See, we can predict it. And the only difference is there's a 2/3. 1 over H naught is by definition the Hubble time. It's a useful time scale that appears in many, many equations. But the 2/3 is a prediction. That 2/3 depends on this very special 2/3 here. And it will be different if you fill the universe with different stuff. So the 2/3 is not a general thing. It relies upon non-relativistic matter. So if you take 1 over H naught is 14 billion years. So then you have to multiply by 2/3. 2/3 times 14. So that's about 9 point something billion years. So it predicts the age of the universe is 9 point something billion years. So it's a little bit wrong. Okay, so that's a whole topic in and of itself. So this is a matter for later where we talk about dark energy. The dark energy will cure that error. Is that all right? Okay. Yes. Well, in particular, yes. There must be something non-Newtonian. Yeah. Oh, okay. So in the way we defined it here, So the short answer is no. So we pulled out, remember we pulled out this scale factor a squared in our metric, and then we had a metric that was static. And K describes the curvature of that static metric. Okay, so like 1 over r squared, where r is the radius of that piece. So, right, so if you like, so as I have it, wrote it here, K is 1 over r squared. But what you're probably thinking about is, all right, but I want to know the physical curvature, not this thing that's just a feature of the static part having extracted a squared. So if you want to call it, I don't know, people don't usually call this notation, use this notation, but if I refer to K physical, not to be confused with the wave number, by the way, okay, this would be 1 over r squared a squared. Remember, we have to put in this a to convert our coordinate x into physical length. So that radius is also static by my definition. It's the a that converts it to a physical length. Okay, so in that sense, it's going like 1 over a squared. All right. So we can put this info back in here. And let's again do a little trick. We'll pull out some k c squared. We'll put in some noughts. I can do that. And then multiply by the time dependence. Yes.
Sorry, we're going back.
No, that's no problem.
So I'm worried about the measurement here. So if physical curvature is what we're actually measuring here, and assuming that it's
That's right.
that has the ability to change with time, then how do we know that our average is really good over that time?
Our average is good over that time scale. What do you mean by our average?
But so if the curvature, physical curvature of the universe changes as that light moves, then how do we know that it's doing constant the whole way? Or do we know that it changes at a small rate?
Oh, okay. So let me put it this way. There's some analysis that goes into converting that theta into this 10 to the minus 3. So I'm saying people have done that analysis. So whatever effects you're worried about has been done. So I'm sort of skipping some steps here. Right? It's non-trivial to measure an angle in the sky and then convert it to 10 to the minus 3. But I assure you people did that very reliably. But yeah, you have to, but you know, yeah, so it's a bit of work. Yeah. All right. So, okay, so we can, if we want, plug this into here. If you know h goes like 1 over t and a goes like t to the 2/3, this whole thing must scale like t over t naught to the 2/3. If I did that right, you can check. Is that all right? Plug this and that into there, you get that. Is that all right? Right, the 1 over h squared will give me a t squared upstairs. And then you have to divide by an a squared, and that will give you a 1 over t to the 4/3. So altogether you get t to the 2/3. Okay. And you see my little noughts are valid because I know that this thing is proportional, therefore, to t to the 2/3. And so therefore, and it matches when t equals t naught by construction. You can also write this factor here. If you like, this is actually nothing more than a over a naught. Okay. So it also grows like a, or it grows like t to the 2/3. Okay. So I do all that because this prefactor, we already bounded it to be less than 10 to the minus 3. That's this fact. So now we can see the bound as a function of time. So omega minus 1 is therefore less than, this is observationally bounded to be less than 10 to the minus 3. And then the time dependence is, it scales like the time of the universe to the 2/3. So that's 1 today by definition, or this is a over a naught. Yeah. No, T naught is defined to be the age of the universe. So I'm not going to set units where the age of the universe is 1. I mean, I could, but no, T naught is just 14 billion years. Is that all right?
I said not of 1 and then like what?
No. Oh, sorry. I said when t equals T naught, this is 1. what I was trying to say. Okay. So what this formula tells us then is that given that we're close to criticality today, if you go into the past, we're even closer to criticality. Okay. And it scales like this. So, I mean, this is, maybe this looks more complicated than what I intended. Let's go back to our little pictures from the first lecture. So we said what I called E equals 0, which is really a flat universe in the general relativistic language, whereas a curve that just grows like t to the 2/3. And then we did E positive, or open hyperbolic universe, was one that matched t to the 2/3 for a long time and then departed. And then E negative, or a spherical universe, was one that went like this. Okay? So what this equation is really just saying that if this is today, say t naught, so it looks, I'm going to exaggerate. So that means we're here somewhere. We don't know. Imagine that is 10 to the minus 3. I've completely exaggerated it, right? 10 to the minus 3 means the fractional difference between these curves and the flat curve. Right? Imagine that little distance there with 10 to the minus 3 of this height. I can't draw that for you to show you. That fractional difference, the percentage difference, was smaller in the past. That's all it's saying, which you can see pictorially here, that they approach one another. But they don't just all go to 0. It's the percentage actually shrinks as well. So they get incredibly close to each other in the past. That's what this equation is saying. So as an example, if I go back to the time of CMB itself, bearing in mind the analysis was done, but at the time of CMB, when the universe was 380,000 years, you could just take that divided by 14 billion years to the 2/3, and you'll get about another factor of 10 to the minus 3. Or equivalently, you can remember that when at the time of CMB, the universe was about 1,000 times smaller than it is today. So that factor there is 10 minus 3. So omega, let's call it CMB to remind us, was therefore less than 10 to the minus 3 times another 10 to the minus 3 from this new factor, 10 to the minus 6. And it just gets wildly smaller and smaller as further and further back you choose to go to make this analysis. So if I were to go back to the time of, say, Big Bang nucleosynthesis, when the universe was like a minute old or so, then you're going to get some ridiculously tiny number. Okay, I won't even put in some numbers, because if I go back too far, the matter analysis, non-relativistic matter is not quite right. The correct analysis actually makes it even worse. Okay, and not worse in the sense that it's ridiculously small, even smaller. Yeah. No, it doesn't approach, it doesn't look like it approaches any particular number. It's asymptoting towards the number 0. Yeah, it's literally this formula. Do you mean at the level of non-relativistic matter, or do you mean if I filled the universe with other stuff? Oh, then all sorts of possibilities are allowed. Yeah, that's right. So if the other stuff includes an early universe phase of inflation, that can completely change this analysis. But that's, what I was going to say is that's kind of a motivation for inflation in the first place. So what I just want to say is the following, right? So if I look at this picture here, we might say, oh, well, I just went back and they got close to each other. What's the big deal? But let's bear in mind that this is an unusual type of prediction. So usually in physics, astronomy, we like to predict, when you make predictions, you usually like to predict the future. There's a prediction, so to speak, of how close omega was to 1 in the past. Now, the universe started at some point, okay? And so it started with some choice of rho and rho critical, let's say, in this homogeneous isotropic approximation. So I don't know where you want to go back. If you just literally go to t equals 0, we can't say much, okay? But maybe we have general reasons why you don't want to trust things to literally t is equal to 0, or the size of the universe A is equal to 0. But maybe you go back to some early time that you might want to start thinking about doing physics. So you could go back to, I don't know, the Planck era or something, when T Planck was 10 to the minus 43 seconds. I mean, as an example. Whatever ludicrous time you pick, omega minus 1 is going to be insanely small, like 10 to the minus 20, 10 to the minus 30, something like that. And so then you would have to say at that moment when it began, let's say it was the Planck time, for some reason, rho, which is the density of the universe at that time, and the critical density, which is defined by Hubble, 1 over h squared, which are a priori independent numbers, it shows those two numbers to equal each other to, like, 30 decimal places or whatever number you want to pick, right? So this we consider to be a bit strange. Let's put it that way. And one can have different points of view about this. But somehow these two independent numbers match to ridiculous precision. This much seems to be the case. Okay, so when we talk about inflation, it tries to address this, what seems a strange thing going on. Okay, so in other words, it's like, in other words, as I said, if it's exactly 11.2 kilometers per second is the escape speed of the Earth, and someone threw up an apple, and let's say it's exactly 11.2. Of course, it's not 11.2, it's 11.2 with some decimals. Let's just call it 11.2 exactly. If someone threw up a ball and you found that they threw it up at 11.2000000 with a 1 at the end after 30 decimal places or something, you might think that was not just some random person throwing an apple. There was some very clever machine that someone wired to do that or something. It wasn't just some random person going like this. Okay, so that would be the analogy. All right, so any questions about this before we move on to the energy momentum tensor? All right, so if you've studied, I don't know which, I mean, certainly in general relativity course, or if maybe some other courses, maybe some QFT course or other courses, you may have met the energy momentum tensor. Who's met the energy momentum tensor? Who hasn't? Okay. Who's very comfortable with the energy momentum tensor amongst those who have seen it before? Okay, so not everyone's comfortable with it. Let's at least enough motivation to say something for everyone. Okay. All right. Okay, so I'm going to put both indices up for a little while. Okay. Make it slightly easier to talk about this thing. All right. So the first thing I want to say, how am I doing on time? All right, is that so this energy momentum T mu is very much the cousin of the current density J mu from electromagnetism. Okay, now this one here, if we were to define it, the precise statement of what this is, okay, let me say the precise statement, and we'll see how comfortable you are depending on your background with this statement. But the precise statement is that if you have any theory that has, okay, well, first of all, you know by Noether's theorem that when you have symmetries, there's some associated conserved quantities. And not only that, when you have some notion where physics is local, there's not just a conserved quantity, like over here, Q, that the total charge is the integral of the charge density, all right, rho C, to remind us of charge density. There's 4 numbers together, 4 densities, J mu, in this case, where the time component or the first component is the charge density, whose integral is conserved, and it has some spatial part, in such a way that there's also a local conservation law. But this is conserved. There's a so-called local conservation law, which means d mu, j mu equals 0. Okay, we'll flesh that out in 1 second. But in this case here, the general rule doesn't, you don't have to say the words general relativity. If you have any system whose symmetries are those of time translation symmetry and spatial translation symmetry. The laws of physics are the same in each moment in time and space. The Noether procedure, first of all, you know that that corresponds to the conserved energy, time translations, and conserved momentum, spatial translations. But that's also conserved in a local sense, the exact analog of this thing. Okay, so there are conserved quantities. Now there's 4 of them. So first I'll write out the total energy. So we're just going to write that as the integral of the energy density, naturally enough. And then there's the total momentum. P, all right, maybe I'll write Pi, or I could write it as a vector. The total momentum as the integral of, I don't know, I'll use pi, for lack of a better name, as the momentum density. And this one is energy density. Okay, so to be clear, these are all can be functions of space-time. Everything. Not this thing. This is just a constant. And so are these. Okay, so the energy momentum tensor that I haven't put on the board yet is the local density that's somehow built out of things like this, the local energy density and the local momentum density and other things, which is the local density associated with time and space translation symmetry. That's the precise statement, even though it's a bit of a mouthful. But the people get the gist of it. Okay, so let me write down the conservation law. Okay, so there's some T mu nu. And now I'm going to have to write down a bunch of stuff. So just like here, the time component of this thing is the density, whose integral is conserved. Here, it's the energy density. We're going to populate up here. And the other sort of, you could say, time components, in a way, T0i and so on, will be this one. So say pi, I don't know what you want to call it, pi 1 or pi x, the x component, if you like, if you're for Cartesians, the y component, the z component, and it's symmetric, so I can put them down here as well. That's where we're populating these things. So this one here, this is to say that T00 is rho, is the energy density, T0i is the components of the momentum density, x, y, z, 1, 2, 3. And the conservation law has to come equipped with a full tensor. Okay, you have to flesh out a full tensor that transforms nicely under Lorentz transformations. So there's other stuff down here, the Tij components, that maybe I'll call these sigma ij just to give them a name. So I'm not saying anything fancy here. I'm just calling Tij sigma ij, just to give it a name. We'll talk a little bit more about how to interpret this thing in a minute. But if people at the very least, you get the correspondence, right? So let's come back here for a minute. The point of these densities do not have the property that every single component of them can be integrated to a conserved quantity. That's not how it works. Okay, if I go back to good old current density, right, that we're all probably familiar with, right? The time component is, or if in that notation, I can write this as rho, comma, J1, J2, J3. Or you could write as a column vector if you want. It's not important for this discussion. So the only part of this thing that integrates up to a conserved quantity is the time component, right? And that's the conserved charge. Nobody talks about the conservation of the vector current. That's what J is. It's the good old vector current, right? It's there if charges are moving, right? There's no such thing as that thing being conserved or its integral being conserved, right? Let's say you have a proton that's moving this way, and that means its vector current J would be a vector pointing in that direction, right? And now let's say the proton bounces off a wall and comes back. Okay, now the proton's going in that direction. Well, its current was not conserved. It went from the vector pointing that way to vector pointing that way. There's no such thing as the vector current being, the j part, the spatial vector being a conserved thing, or its integral being conserved. It's the time component. Okay, now this local conservation law, we can look at that for one more minute to flesh it out. It's this particular contraction of indices adds up to 0. And if I write that out, I'll plug this in here, I'll write mu equals 0, so that's d time derivative. That's mu equals 0, 0, is dt rho c. I hope that's all right. And then I add d, we'll call it di ji. I equals 1, 2, 3. So I just rewrote out that expression. That all adds up to 0. Okay. So if I rewrite this thing, we could just be 100% clear. D rho dt, if I just make it manifest what I mean by dt, equals, I move this to the other side. So diji. Anyone know a good mathematical name for diji if I were to write it in a slightly more compact way? Yeah.
Gradient of
A gradient of j. That's okay. That's good. Is there another name for a gradient of a vector? What do we normally call a gradient of a vector? Sorry? Nothing fancy. Divergence, yeah. Do you agree with that? Morally, a gradient of a vector is you could call it that. But it's usually called the divergence. So I'll write it as div j. Okay. Let's just stare at that for a minute. And this is local conservation. So local conservation, just is the statement that not only is the total charge conserved, right? It just cannot be that the way that total charge is conserved is that a charge disappears from here and suddenly appears there. That's not allowed either, even though that would allow for total charge conservation. It has to be that the charge is, as it were, conserved locally. And so this equation expresses that idea. So let's say the left-hand side is positive. So say here, the charge is growing. So d rho dt is positive. So somehow the charges, let's say we have positive charges, they're growing. It's saying the only way the charge here could grow is it equals minus the divergence of something. So you have a negative divergence. That means negative divergence, it means stuff is flowing in. That's when you have a negative divergence. So charges flowed in so that the charge here could increase. That's just what this equation summarizes. And similarly, if d rho dt were negative, it must be that charge has flown out, has a positive divergence of charge. That's all that equation says. And then we can double check that this equation then, if we start here, self-consistently implies what we want, which is that the total charge is conserved. So can anyone tell me, if someone handed you that equation, how would you prove that this is a conserved quantity? How would you prove that? If you didn't know this, but you knew that. Any thoughts on that? Yeah. Right. Well, yeah, that's right. But we have a time, there is a time derivative here. You mean you want to take time derivative of this one? Oh, yeah. That's fair. Yep. We could directly take that. So if I take dq dt, we could do it that way. Oh, that's okay. Let's try your strategy. I'll write dq dt. So this is d dt. If we say the definition of q is the integral of the charge density. Now, you are talking about straight or partial, but actually if I move it inside the integral, now it has to be a partial derivative. Is that okay? If you put it on the outside, it's a straight derivative. Anyone know why? I mean, if you write partial if you want, but there's a good reason I wrote straight. Anyone tell me why here I wrote a straight derivative? Sorry, speak up a little. But I just couldn't hear. Can you? That's right. So here rho, well, we have to be careful. So rho in general is a function of space and time. Let's say I have rho like this. So we're going to imagine there's some stuff. It could go negative like this. So this could be a function of x, and it can wobble around in time, such a way that it obeys this rule. So the difference here is that in general, when you have a function of space and time, we can act on it with partial derivatives. But when I move the derivative in front of the integral like this, once you've integrated over space, whatever this thing is, whether it's conserved or not, that thing has to be only a function of time at most. Because you've removed the spatial dependence by integrating over space, right? So you could write a partial there, but you might as well write a straight derivative. Okay, now this thing here, we know obeys this rule. So this is minus the integral of the divergence of J. And then under some nice conditions, that thing I claim is zero. So what might be a condition where that thing on the right is zero? Why might we argue that this thing actually integrates to zero? Okay, but sorry, what I meant was suppose you knew this, right? So the task is this. I want to double check that it implies charge conservation, just so we're sure. We could think of this as being a slightly more fundamental and general statement than that. Now, this implies that, but that does not imply this. Because as I said, if you only knew charge was conserved, you could imagine charge disappeared here and appeared there. So this is a more general fact. Not more general. This is a more precise statement. This is a consequence. But we haven't quite done the proof yet. What about the divergence theorem? Maybe we should use the divergence theorem on this thing. So this thing here then equals minus, I don't know, d2s n dot j, where this is some surface over which we integrate. And we're going to imagine that out at large distances where the surface is, the stuff is going to zero. We have to imagine that, or we cannot make progress. Rho, and similarly J has a similar shape in the sense that it's asymptoting to zero. So you want to imagine you have a bunch of charge in the room here. Maybe there's a bunch of stuff here, but away over there, there's nothing. Asymptotically goes to zero. So that means that when you evaluate this integral on the surface, you just get zero. Okay. So then we proved that the charge was conserved. Okay. Now you have to make that assumption, or the charge is not conserved, right? If I have a box and you say my surface is the surface of the box, and you just allow the charge to leave the box, do you think the charge inside the box is conserved? No. So you have to make your surface big enough that it encloses all the stuff. Enclosing all the stuff means that the charge at the surface would vanish, and the charge density and its current density relatedly vanishes on the surface. Yeah. Well, the assumption is that this surface is so big that out here, really the precise statement is that J is zero on this surface. You can think of rho vanishing there too. So there's no stuff out there. Sorry, you have to speak up. I don't know if I'm going deaf or not.
Then like the sphere needs to be very big and then J will be zero. Is that what I'm
No, we're just saying that essentially yes, but we have to imagine that there's charge that's sort of localized and there's nothing out there. If you just say there's charge that just keeps on continuing throughout the universe, which is not a crazy thing to say, then whatever surface you lay down, there can be charges moving across that boundary. And you cannot, strictly speaking, say the charge is enclosed. That's just the way it is. So whenever you talk about charge conservation, you have to imagine the region that you're adding up is all there is that's relevant to what you wish to discuss. And there's essentially negligible contributions from outside, or that strictly speaking, it's zero at the surface. Okay. So, all right, so now we play a similar game over here. Where can I put this? All right, so let's do the case for the energy momentum tensor. Okay, so the statement of the local conservation is d mu T mu nu equals 0. That's the exact analogous statement. And this one now has a floating nu index. So we contract on mu, just like I wrote d mu j mu is 0, but it has a leftover nu index. So for each nu, this is true. So these are 4 conservation laws, because I can set nu to be 0, 1, 2, or 3. Okay, so let's just check on nu is equal to 0. What does it give? So I mean d mu t mu 0 equals 0. Let's write it out. So I get dt t 0, 0 plus di ti 0. Okay. T 0, 0 is the energy density. This is rho, and there's a dt. I can write that dt or d rho dt if we wish to make it really clear that it just means a time derivative. And then I have di ti 0, which are these spatial components. So that I called pi I. That's the momentum density. Okay, so now I hope you'll see that this equation looks completely analogous to our previous equation. Rho is just playing it's like rho instead of rho c, and this 3-vector momentum density playing the role of the vector current j. Otherwise, it's the same. So I could even write d rho dt is minus the divergence of the momentum density. So this is the statement of just local energy conservation. Okay, so I hope we don't have to redo this derivation on the top right there at this point, I imagine. You can imagine that the integral of this thing is indeed a conserved quantity by the same derivation. We're all cool with that? So that self-consistently, we know that the integral of rho is indeed conserved, so this checks out. And then this statement physically is identical to what we said previously, right? It's just saying that locally the energy can grow if there's an inflowing momentum that comes in. So there's a momentum of stuff comes in, stuff transports itself inwards, an inward divergence of stuff. So locally the energy can grow or decrease vice versa. Yeah, so local energy conservation. Any questions about that? All right, and then we have yet one more equation, one more local conservation law. Well, 3 of them actually, but a 3-vector worth of conservation laws. So let me, in this equation here, pick nu to be a spatial index. I'll call it j, right, j1, 2, 3. I'll reserve I for a dummy index. So I get dt, well, let's write it out. d mu t mu j equals 0. So this is dt t 0j plus di tij. I carefully separate out my i's and j's. T0j is the momentum density. So this is pi j ddt equals, we'll put it to the other side, why not, minus di, and tij, I just called it sigma ij at this stage. Those are just the spatial parts of this thing. So we have this rule. Okay, so this means that the momentum, the local momentum density can change. Again, I don't want to rederive, but even if this may or may not look like a divergence, once you have a derivative acting on some quantity, you can still use some kind of version of divergence theorem or fundamental theorem of calculus to know that this thing will integrate up to some boundary term, so it vanishes if we do an integral of this thing. So we can rest assured integral of pi over space is a conserved quantity, which is the total momentum. You integrate momentum density. But we can try to interpret a little bit more what this equation is saying. Somehow the local momentum density, if it's changing as a function of time, if it's growing or decreasing, is somehow related to some derivative of some funny 3x3 matrix, sigma ij. This one's a little more funny to think about. Oh, I didn't give this thing a name. So all these other things I named, but let me say in a moment, if you've studied fluids or something, you may have met this thing. This is sometimes called the stress tensor, even for a non-relativistic fluid. Although some people call the whole 4x4 thing the stress tensor, so then it doesn't say much. But anyway, the context of non-relativistic fluids, for example, you may have met the stress tensor. Let me give you a simple example, which is actually very relevant for us in cosmology. So imagine sigma ij, something very nice happens. Imagine it happens to be controlled by a single number. Let's just be simple for a moment. And then we'll say some words about the more general case. So imagine it's just the identity matrix times some number, which we'll call P, very suggestively. So in other words, it's just P, 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 zeros everywhere else. Let's organize our thinking for a minute. Okay, so that's sort of the simplest case you could imagine. It's just proportional to the identity, this matrix. And then there's some function. Remember, these are generally functions of space-time. So the P can be some function of space-time. Then this equation in this special case will give us that the rate of change of the momentum density is minus just the derivative of P. Right? The Kronecker delta means that I must equal J, so I replace the di by a dj. See the J's, there's a J on both sides. Okay, so this is now really a gradient. Okay, so this one I like to call that thing a gradient. Is that all right? So this equation here, even though it may look a little funny, is actually a very physical thing. If I identify P as the pressure. Okay, so let's say you have a fluid, right? And you tell me that its momentum, of the local momentum in some region of the fluid is changing. Well, you know, the total momentum is the same, but locally the momentum can go up and down as long as it's compensated at some other point. Momentum, you know, by Newton's law can change if there's an applied force. And in fluids, a good old force is a pressure force. So you don't get a force from pressure per se, you get a force from pressure gradients. Differences in pressure is what creates forces. Okay, so let's say like you have a pipe, and there's say a thick piece of the pipe and then a thin piece of the pipe. Bernoulli says something like here, which way does it go? The pressure is small and then the pressure is big, and that's a gradient that drives the fluid to go from moving slow through the thick piece to moving fast through the thin piece. Okay, so that's just the good old statement that pressures drive forces in, say, a fluid type of system. But generically, that's spatial part or the diagonal part of this stress tensor, we always call it the pressure. Okay. So this happens, I don't know how much time we have, a few minutes. But systems that have good reasons I can flesh out in a minute, that have isotropy, the sigma ij will collapse to this form. I can flesh that out if there's time. If not today, the next time I'll make that clearer. Okay, so fluids that have isotropy, this is actually a correct formula. But systems that do not have isotropy means that the more complicated part of sigma ij, right, this is some 3x3 symmetric matrix. So in general, it can have 6 components. Here I've given you one thing, P, but there's 5 other things in general to control this thing. In some way or another, all associated with the possibility of anisotropies in the system, as we can flesh out. So for example, if these 3 numbers here were different, you would say the pressure in that direction is different than the pressure in, say, the X versus Y versus Z direction, if these were different numbers. And then these other ones involve some kind of X, Y, X, Z mixture. They're slightly more complicated yet again to interpret. But are people, at least with that special case, comfortable with this thing? Okay, so that's what these local conservation laws are all about. And whenever you have some local conservation law, you have to, as I said, fill out the things that are conserved. So it's the integral of rho that's the conserved energy, the integral of pi is that's the conserved momentum. You always have to flesh it out with these other pieces to build a local conservation law. right? Just like you have to flesh out the charge density with the current vector density to have a conservation law. There has to be some flow of these things into this other stuff, even though the integral of this is not the conserved thing. Integral of, well, anyway. Questions about this? All right, so we may not have enough time to do this justice, but now I also want to give you a formula for the energy momentum tensor for a gas of particles, classical particles. Yeah, so you can imagine writing down this energy momentum tensor for any system. You could have electromagnetic fields, all sorts of stuff. As long as the laws have time and space translation symmetry, you can define this thing. But let's call it, say, a gas of point particles. All right, so the T mu nu is something interesting. So let's say here's T, here's X. There are point particles moving on some world line. That's one, but there are going to be many of these, potentially, a gas of them. And this T mu nu, these are the kind of things that well, we don't have to be super duper experts on it per se, but it just so happens that with enough experience, these are the kinds of things you can write down with some very general arguments without knowing too much. So you have to build a quantity that, first of all, is some tensor, okay, with two indices. And as a particle moves along, there's not a lot of vectorial stuff you can attach to it. For example, you can attach to it its velocity vector. So let's define that. So what's usually called the forward velocity is dx mu d tau. Right, so x mu, I'm just locating this particle. If this is the nth particle, we'll label that the location of the nth particle x sub n, and d tau is the proper time associated with this particle. Right, so it's the clock in the rest frame of that object as d tau. So really, actually, every particle has its own proper time. So I really should write tau sub n, but it's going to get boring. I'm not going to bother to write those n's, but you're welcome to put an n there. So that's a forward velocity. So if I was to try to write T mu nu to carry the indices somehow, I might write dx mu d tau, dx nu d tau. And in some sense, those are the only vectors in the game. So it's only a product of them could I even imagine building some tensor. But this thing here is also a local density. Okay, so local density means that this is a quantity that hits where the particle is and is zero where the particle is not. Right? That's what these densities do. So this thing is going to be some kind of delta function. Does that make sense? It has to be a delta function that hits where the particle is. Right, so you could try delta 3 x minus xn that hits where the particle is, and I should sum over all the particles n. So I could try this, but when you throw around 3D delta functions, you could run into trouble if you just guess like this, because a three-dimensional delta function is not quite a good Lorentz scalar. Okay. So, you know, delta function has a property that integrates to 1. You do an integral over space. But in relativity, you have length contraction. So in another frame, they may not say, it doesn't integrate to 1. It integrates to 1.2 or something. There's some funny gamma factor. Okay? So this is not quite a good Lorentz scalar. There is, however, a safe thing, which is the 4D delta function. Four-dimensional delta function. By that, I mean you write delta t minus tn. You can wrap your mind around that, times the 3D delta function. And I won't prove it here, but rest assured, the 4D delta function is a good Lorentz invariant quantity. So when you go to another frame, there's two things. There's length contraction and time dilation. And let's say they both manage to compensate each other. So this is a good Lorentz scalar. Now, You do not want to say that the objects only live at a moment in time. That would be a particle appears and disappears. So I don't want to literally write that. So I know that the particle persists for all time. So you have to put an integral here over time. And to be safe, I'm going to write d tau, because that's a good Lorentz invariant quantity. So these arguments may seem a bit slick if you're not used to them, but these are the kind of ideas that if you didn't know anything, if you didn't look it up in a book, you would be able to write it down. This is a 2-index symmetric object, which is what we need. These are vectors, because dx is a vector, and proper time is a scalar. So dx d tau is a vector. That's a scalar, that's a scalar. So in a sense, this is the only option on the table to even construct C B nu. With one exception, I could always put a number in front. If you multiply a good tensor by the number 2, it's still a good Lorentz tensor and so on. And so I should put a number here. Let me see how much time I have. Okay, 2 minutes. So the correct number, well, I'll just tell it to you now, is actually the mass of the particle. I'm setting units at the moment where C is equal to 1. Not sure I could remember where the C's go at this point. So maybe we have just enough time to tell you why T00, that had better be the energy density. Is actually why I know that M there is a good choice, is the correct choice. If I put some other number, I will not get the energy density. So let's try to evaluate T00. Right, so, okay, so T mu nu. Well, let's just start with T mu nu for one moment. So if you're with me, you know that this is a Lorentz tensor. And there's a lot of funny manipulations we want to do. I have 1 minute to do. But for example, we see a d tau. I can sort of, if you like, trade it for dt, right? You have upstairs d tau and a downstairs d tau. You get it? So I could trade it for some other variable. So it's actually going to prove to be convenient to trade that pair for dt, dxn mu dt. I kind of multiplied and divided by d taus and dt's, if you like. That's a kind of chain rule, if you will, but it's kind of simple. And now I'll keep the rest for the ride. And then I'll write out the delta function. Okay. I did that because I know that the time integral of the delta function is 1. You don't want to write the integral with respect to proper time is 1. That's not a good idea. But the integral with respect to t of delta of t is 1. Nothing fancy. Okay. So this stuff integrates to 1. So then T mu nu is sum over n, mn. Now we're back to a good old 3D delta function, which you expect for a density. And then there's some prefactor. dx mu dt, dx nu d tau. Okay. So I just say one thing and then we can go. So let's say we look at the 0, 0 piece of this thing. So T00, sum over n, mn. The time component is dt, right? x0 is t. So this factor is dt, which is 1. This factor is dt, d tau. Okay. Now maybe, does anyone remember what dt, d tau is from your special relativity courses? There's some inertial observer thinks the time is t, and there's a proper time tau. Anyway, this is the gamma factor. Of that particle. That's why I should write tau n if I was to be complete. So T00, we see a sum over n, mn, gamma factor, and a 3D delta function. And if I was to bother with my factors of C, to be sure, this would have a C squared here. So you see, this is the energy of a particle, m c squared times a gamma factor for a moving particle, right? You're all familiar with that. Energy is m gamma c squared. So this is indeed the energy of a regular particle times a 3D delta function. Okay, so the 3D delta function just guarantees this is the energy density for point particles. It integrates to the sum of the energies, which is the total energy. Is that clear? All right, and then we can easily check at the start of next time, T0I will be the momentum density. And then the Tij's, which are a little funnier to interpret, the sigma ij's, we will learn what their values are, because Lorentz symmetry predicts the whole structure of the matrix. All right, we'll see you next time.